I'm going to be doing a video call, so. Oh, there we go. My goodness, my first stream, I have no clue what I'm doing. Okay, this is it. Live streaming. Very cool. I'm going to also record this and put this on YouTube, in case anyone's not able to watch, because I promised some people on Twitter that I would kind of do a video of this talk I gave at a local meetup. So here is going to be an introductory to computer science data structures, super simple stuff. List styles, what I'm thinking about, linked lists, queues, decks, and stacks. And I figured what I did in the talk was like I pre-wrote all of the code for the linked list, the queue, and the deck, and the stack, and I wrote them in like vanilla JavaScript with arrays, but I also wrote them using the linked list that I wrote in JavaScript. But I figured because this is a stream, we can get a bit more in depth. We might as well do our own linked list from scratch and then use that to rebuild the queue and the deck and the stack afterwards once we kind of understand what's going on. I don't know if you can see this URL, but you can go to this site and like get the slides for the talk, although I'm not going to be going through them or using them too much. Instead, I feel like we should just dive in to running a linked list and what that looks like. Let me just figure out if I... Wow, so many windows going on. Okay. I'm sure people are familiar with VS Code, so I'm just going to use that. Everything's all in one go. And I'm sorry if my typing is slow because I have a broken wrist. So let's start off. So there's a few things we need when it comes to a linked list, and we'll talk about a little bit what the structure of it is. So when I think about a linked list, you have like a JavaScript array, and you have elements in it, 1, 2, 3, blah, 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 blah. What we actually want to translate that to, or what a linked list is going to look like, is having individual, we call nodes, holding some sort of value. And each of those nodes, they're connected. So we have like 3 of them in our case. They're connected by a pointer, what we say. So this, or a reference. We have like an arrow that goes towards 2, an arrow that goes towards 3. And then in order for us to know that this list, this linked list, is ended, the last element has to go to null. So this is kind of the same data stored in 2 different data structures, a JavaScript array and then a linked list. So we can put any type of data we want in here. Let's say we want to have like a string instead, blah, blah, blah. That's fine as well. I can go there. But for now, just use numbers. It's a bit easier. And you can obviously have as many items in this list as you want. You can just keep adding them on to the end, as long as they keep pointing arrows, blah, blah, blah. And it can grow forever and ever and ever, as long as you have some sort of null at the end to let you know that the list is finished. And we can go over a little bit at the end what the value is of having like a list like this and storing them instead of using an array. Not that we use them too much anymore, and often if you are using one, they are written by somebody else and not this crappy implementation that I'll be doing, but at least nonetheless it'll get you some understanding of what a linked list is. So let's start off, kind of go through this, like to get the structures of this that we'll need to program it. And I'll be writing this in JavaScript and in Node. I'll be using Node. Oh, I did a spelling mistake. 10.16 in case you're wondering and if something's not working on your machine. All right. First thing we need, obviously, in order to store this kind of list is a node. So let's create, I'm going to use classes, I think, for this. So we'll call this a node. As opposed to we could use some sort of factory function or something like that, but instead we'll use classes. And then we can have a constructor here. Whoops. Oh my goodness. Okay, perfect. And the constructor takes 2 things. So we're creating a node for this list. We need to be able to store the 2 pieces of important information. One is the actual data that's there, and the other one is who is next in the list. And we call this kind of the next pointer, the next reference. I'll talk a little bit what references mean and how they work in JavaScript because they're a bit different. Okay, so we take in those things, we have some data, That's always going to be there. Now, the next reference, we don't always need it. Because, look at like number 3 right here at the end, you have null there. So instead we'll just default this, so we can make it a bit easier, to null. And that way when we're creating a node for the end of the list, we don't have to worry about specifying null in there. And then we'll just keep those pieces of data stored locally, something like this. There, and then keep the next pointer as well. Boom, and then, whoops, that's not gonna work. There. Oh, my prettier says, oh yes. Naturally I can't, that's not valid JavaScript. There we go. Perfect. So this is a simple, super simple node, and we'll be using that to create these lists. Now the other thing we'll need besides a node is the actual linked list itself. Ooh, linked list. There, and it's going to have a constructor as well. Now I'm going to keep this super simple. Actually, I don't even need a constructor. Do I? Yeah, no, we don't even need a constructor. I'm going to keep it super simple and just have a static property on this. It's going to be called, I don't know, list, maybe? No, I lied. I'm totally lying to you. It's going to be called head, and it's going to be equal to null by default. Can I not do that? Constructor. I'm too used to writing in Babel. Maybe I have to do this dot head equals null. There, okay, so when we create a new linked list, we set this head variable, whatever that means, to null because it's an empty list. And that's literally all we need to start off our linked list. Now obviously we're going to need some functions to add and remove elements from it. So let's just put those in there. So we're going to have an add function to add some elements to the list. Maybe a remove function to remove elements from the list. I'm going to write this one, so it's super handy, print, just so we can visualize a bit better what the linked list looks like. Add, remove, and then maybe the last one is like if I want to see a specific element in that list, we use get. So we'll implement those functions. We'll start with print first, and so we can see what the linked list looks like. And we want to be able to use this by saying like I want to create some sort of const linked list, ll, is going to be equal to a new linked list. Good, and then we can just console log it to see what we get. Whoops. Perfect. Node, linked list. Boom. There we go. I'll find a way eventually to make this head variable not accessible. Like we want to just keep it here as a static element, maybe only with a getter as opposed to just having it accessible because we don't want people to be able to change it outside of there. Or we can just change this to be a factory function instead and then use a closure. But for now, let's leave it there. It's accessible there. That's fine. Good. And then we have some functions on this, like add. It's going to be a function. Boom. You can see down there. Function add. And obviously remove and those kind of things. But they don't do anything yet. So I called like add, and I want to add number 1 to the list. That's not going to do anything except for return undefined, because calling that function is going to return undefined. And then if I console log afterwards the list again, it's not going to change. Still, the head is null. Good, okay. So before we get into writing any of these implementations, we kind of have to understand again what this structure really is about. And how we kind of navigate these lists, because it's not like we can loop over it like a normal list. Indexes, although they can exist, they don't really exist, right? We can't say, get me the value at index number 2 in a linked list. Sorry, index number 2 would be over here, value number 2. Because we don't have one structure holding all the values. So JavaScript array, let's just create one right down here at the bottom. So we do console.log, some JavaScript array. And we have like 1, 2, 3 in there. If we print that out, we have a single structure that kind of holds all 3. And if I do like, how can I do that a bit better? Maybe I should show that we have like a function directly on this list. Ooh, I bet I know. Object dot assign, like this. There we go. So I'm assigning an array to an object. So we should get this nice print of, oh, it's exploding. Assign is not a thing. There we go. I spelled assign right this time. Good. There we go. This is what we get. That was not exactly what I would love to see, but that's fine. We see like we have an object now of where indexes are like 0 pointing to 1, 1, the index of 1 pointing to 2, and the index of 2 pointing to 3. And if you were to look at this object in more detail, you would see it has functions attached to it as well. And so you can see that this one object holds every value associated with the list, 1, 2, or 3, or however big it gets. Right? If we add more elements, we get more keys into this object. So you have a single object holding all of the data that that list will ever have. A linked list, now again, we won't be able to print this just yet and look at it kind of executing, but it only ever holds one piece of data, and that is the head. The head is just, which one do I start with? Like, where is the beginning of my list? Because again, as a linked list, I don't really know about all of the elements in it. I only know about the first one, which means I also don't know things like how long it is. I also don't know things like, like the bounds are, where the end is, which values at the end. And that also means I don't know which value is at position number 2. I don't even know if I have a position number 2. All I know is this is my first one. So that's what the head is for. It's really important. So when we go to add something, we can start maybe by doing, if we add some data. The first thing is if I don't have anything, so if for some reason my head is still null, if I don't have a head, not head, then I need to make the new data that head. But I can't just do something like this. I can't just say, the head is equal to the data. Boom, done, we've done it. Let's just console log that, so ll.add 1, and let's print the list, console.log ll. Oh my goodness. I'm blaming this on my broken wrist, my terrible typing. Boom. There we go, the head is 1. What's the problem with this? The problem is that, I should probably give some time for people to answer, right? The problem with this is that 1 can't possibly have a reference to the next item in the list. How is 1 just a piece of data? It's a number. So we can't have it say, I don't know what number 2 is. It has no idea. So instead here is where we have to use our new node function and pass that data to that. So we're starting to form a linked list a little bit. And if we run the add again, boop, there we go. So the new head is actually a node. And that node contains data of 1, but it also contains that next reference to whatever item is next in the list. In our case, we've only just created like a list here of 1 and then the end. And as I said before, the end is just default points to nil, so we know when to stop. So let's go ahead and add another. Let's say we want to add 2. So we want to have a list of 1, and then that one points to a node that has 2. We do that. Let's run that. Boop, nothing happened. We still have data in there. Next is null. But why is that? Because our only logic here is if the head is empty, which is not anymore. The reference, we've changed it. It's not empty. It's actually a node. So the value has to be whatever the last node is in the list. In this case, it's just the head again. We have to replace this null value here with a new node. And the way you do that is it's really tedious. And you'll see that every operator in the print we do the same thing over and over again. But this is how you traverse, or you walk through and get the index of an item in the linked list. So we start by declaring some variables. So we'll say let the current node equals to this.head. So we're going to start iterating at the head. And then we'll say while, but you don't see while loops in JavaScript very often. While the current node is not equal to null. So if we haven't hit the end, I'll just make sure that's a strict equal. If we haven't hit the end yet, keep walking, and then just shift whatever one I'm holding to the next one. So we'll say the current node is equal to the current node dot next. Now we know that immediately, because this one for our first value, right? So we set the head here, which means that we're going to have a value of whatever this is below. Just copy it here. And then as soon as we get into this, you can see that the next is going to be null. So it'll only go through this loop once. Current will be null. Ooh, that's a problem. How are we going to actually add a new node on if current itself is null? This is a problem with looping through linked lists. You can't just actually keep track of one thing. You have to keep track of previous. This one defaults to null. Making sure you're looping through and keeping track of this one, passing it off to keep reference to that old one until you hit the end. I mean, there's other ways of looping through this list, but this one I feel like is going to be a bit simpler to grasp. So obviously we're going to do this, but before we do that, we're going to assign and pass these off. We're going to just make sure we keep the previous one is equal to the current one, because then we're going to change the current one. There we go. So we have two hands now, and we're kind of like passing back and forth these nodes as we walk through the list, not caring about what we've passed, and then not caring about really what's in the future, just the one ahead of you. And then when we get down to the end of the list, because we're going to be adding a new node, we should have two values here, and we can console log them just to show. And we'll have the previous value, and then the current value, which should be null. It should be like the end of the list. Previous, I should probably call that previous node, right? Just to be consistent. Previous node. There, all right, let's run it. Boom. There we go. So you can see like the previous one is the one we're on. And then, oh, I see what I did there. I said, why is it printing twice? That doesn't make any sense. Because even though I did this stuff here, I didn't return afterwards, and so it assigned the head and then continued to go and do this. So you should get one print now. There we go. Okay. Let's clear this out. Oops. Boom. There we go. So we walk through, we get in here, we set these variables, we do our loop, we set the previous node to the current node to the next reference, which is null. And then it ends, because current is null. And we get the head now being the previous one and the current one being empty. And so then what we can do is we can say, okay, I know I have the empty one, and I need to replace this empty one with a new node, the new piece of data that I'm adding. And this one has to point to that. So right now this one's pointing to null, but I need to replace that with a new node. And how we do that is we say, okay, well, the previous one has that .next value. And right now it's pointed to null. You can see it right here. It's pointed to null. We just need to change that to point to some new node with whatever data we have in it. And in this case, because we're always adding to the end, we can default that next value of this node as well to be empty. We don't care what it's pointing to at the end, because current node is also null. So we can leave it at that. So previous.next, the reference to the previous.next should be replaced with a new node, and we should get an even deeper nested JavaScript structure down here. So let's just run this. Boop. Oh no. Right, I called it previous node. Silly. There we go. Okay. Boom. There we go. So we have data number 1, and it has a next, which is a reference to a new node, which has data number 2, and then its reference to next is the end of the list. And if we go back to our quick example, so we started off with this, then we added 2, which kind of shoved a new node in here, and that new node now points to the end of the list. So that's kind of the structure we have, and let's do a nice print so that we can see that sort of structure as opposed to just console logging this nasty mess here. And this is where we start to see that looping through, passing nodes back and forth happens a lot. It gets a bit tedious. So we still need to do the same thing, right? All we have in terms of the linked list information is the head node, which means that we have to walk through and pass each node to each other as we, oh, Brian! What's up, Brian? Yo, Beats. He's just chatting with me, I guess. Listen to me ramble. Oh, how do I Twitch stuff? There we go. Brian. I hope you're not listening to me blab on for too long, Brian. All right, back to this. Printing. Right, so we got to loop through, and what we want to do is print out this sort of structure of having like a node, and then that pointer, that arrow, that reference to the next one with the square brackets, and then eventually hitting null at the end. So let's go down here and say instead of console.log, we want to do like, whoops, ll.print. And that should give us a nice output. And let's run it. Obviously nothing happens. It's giving us undefined. So we'll say, okay, let the current node, whoopsie, equal to the head, this.head. Again, starting at the head, got to pass them along. And then while, this one we don't really care about maintaining the previous one, because we don't really need to know where to point things next. We're just kind of walking through it and printing out where we are at the time. So we can say while the current node is not equals null, it's not the end of the list, we can just do process.std out, standard out, dot right, I think it's right. And then I'll use some string interpolation here, do square brackets. Inside that, we're going to set whatever the current node is, dot data. So print whatever the data is, then we're going to print an arrow after that. And so just in case you're wondering why I'm not using console log always adds like a new line. I want to write this all in one straight line until we hit that list, then we can do a new line. So that should do that. It's an infinite loop now because I'm not changing the current node. It'll never be null, so at the very end of that, current node equals current node dot next. That's where we pass those hands along. We pass the nodes to our hands. It's kind of a weird, doesn't make it, I hope it makes sense. Just shuffling my hands in front, hoping you understand what I'm talking about. So this will go until it's null, and then just end. So I can just run this and see what happens. There we go. 1 and then 2 and then nothing, which is good. But at the very end, we want to make sure that we have that null, just so we have exactly what we were printing out. There we go. And then we can pass in null. It's the end of the list. You're pointing to null. You have no reference at the end, and then a new line. Good, okay. So we run that. Whoops, didn't run anything there. Run this. Boom, there we go. So 1, 2, null, and if that's so because we added here 1, and then we added 2 to the end of the list, and if we add some more, 3, 4, you get a nice list of 1, 2, 3, 4. There we go. That's how we like basics of a linked list, I guess. We can go into some more complicated things, like what if I want to add 4 before number 2, or I want to add something at the beginning of the list. I want to specify, okay, I want to add number 5, but I want to add it at the beginning, or I want to add it in the second position. We can do something like that. So obviously this is just going to add at the end because we haven't implemented anything like that. Nothing crazy here. But let's change our add function so that whatever we give it an index, it's going to add that node before it. So it's going to create that new index, right? So we can say before, and then we'll just give it a default of null. So this function is going to get way more complex now, because not only do we have to like loop through these nodes and like walk through them as we go, but now we have to keep track of, have I hit this index, if it exists even yet. So let's do that. Right. Let's create some sort of counter. We'll just call it index. Makes a bit more sense. And it starts at 0. Or, even better, let's start it at before. And then we can count down. Does that make more sense? We'll see. We'll see if I can do that. So we're going to loop through the current node, and while that's not null, like while you haven't hit the end of the list, or the index, and we'll decrement that every time, is greater than 0. So we want to continue to loop until we reach 0. Now this is going to be a bit odd, right? Because, well, before is null if we don't add anything, and then is null minus minus less than 0, or greater than 0. I'm not really sure what that's going to give us, actually. If I do null minus minus. Yeah, okay. Yeah, it's like, oh, if I could assign it to a variable, though. Now I'm just playing around. I'm just curious. If I do let index equals to null, and then I do index minus minus. Oh, it gives 0. Look at that. Beautiful. So I guess it coalesces null into 0. That's wonderful. I was expecting not a number, but that's even better. I mean, not ideal. I guess the default is if we do add, we want it to be the end of the list. We don't want to like add it normally. We don't want to add it at the head, which is what would happen. what happen would be we'd come in here, we'd say, oh, well, this is null minus minus, which is 0. Is that greater than 0? No, so I'm not going to continue doing this while loop. And I'm going to go straight into modifying the data. We want to just go all the way to the end. So I guess we can say, like, if that or you have a before value and the index is greater than 0. If you don't have, that might break. This might break. We'll see. Okay, so we added 5 at position number 2. But it might break before all of those anyways. We'll see. Here we go. Let's run it. Ah! That wasn't it. Oh, it broke. Actually, this might be okay. This might be a good amount of break. Can it read property next of null? So I have a feeling it went too far. It said that this is not false yet. That doesn't make any sense. What happened? Current node, so it says this here. Current node is null. I think I had to say, make sure these are both true. Neither of those can be true. That might be better. Okay, this is better. This is more what I expected. Now, I think what's happening is it's trying to add them all at the beginning. And what happens if you're trying to add something at the beginning, as if I'm saying to do like 5 added at the beginning, position 0, instead of position 2, is that we don't loop at all through here. We come in here, we say, well, yeah, the current node is not null, but we have a before, and its index has already failed. Either we don't have a before, or the index has already failed, like it's already too big. So we skip this all together, and we come in here and say previous node, not next. But if we don't run this code, I'll just collapse it. If we don't run this code, what value is previous node? That's null. Now this is a valid operation. We want to say that's like adding something to the head. So we want to say like if previous node, if not previous node, let's put a comment in here. I want to be the head. We need to do something fancy, which is say this.head is equal to the new node, creating a new node here with that data. So we're getting a new head. But then if we just assign that, we lose the rest of the list. It's gone forever because we have nothing pointing, no references to it. But instead, we do new node and then data, and they say, okay, well, we have this whole entire other list, the old head, replace that. So we actually want to say take the rest of the list, this.head, and attach it. This is that, if we go back up here, to that node class. This is that next second reference we haven't been using. But now that we know the next pointer, because we're giving it that head, we can create a new node like this, which should maintain the list. Now this is the only case the previous node will be null. So literally else, every other case, you can just assign previous.next. Now I think there should be another problem that'll come up here, but for the meantime, this should be okay. All right, let's see what happens here. Here's my guess before I run it. My guess is going to be that instead of having 1, 2, 3, 4, I'm not even sure what's going to happen here, we're going to have 4, 3, 2, 1. Here we go. Oh, crazy. Yes, actually, this makes sense. So we started off with 4, 2. I don't know why 2 is gone, actually. That's interesting. 4, 3. No, I do know why. Okay. Yeah, because I wanted to replace it. So what happened was we started adding these all at the beginning now. So we push them in like this. I'll just do a comment so it doesn't yell at me. We started by 1. That goes to null. Then we pushed in 2, and because I kind of broke our loop, and it never actually goes into our loop, it put 2 here. And it did this all the way along. So 3, it added, and then it added 4. And then we got to 5, and because there is actually a value here, it actually went through the loop and stuck 5 here. The problem is that we didn't give it a value, so it did null here, and that means that this piece of the list just kind of got lost forever. Those 2 elements we don't know about them anymore, and they got garbage collected by JavaScript. Dead, gone. I can just go. There we go. Boom, dead list. So there's a few things broken here. Let's start by fixing this 5 so we don't end up losing all the bits of the list before we go into writing a better code that doesn't skip this loop almost every time. So the reason was that when we created this, we didn't hit this because we don't want to be the head. We actually were given an index that went into the list a bit. I'll copy this line here. Whoops, that's not it. Boop. Copy this line. So we have this list here. Nothing's deleted yet. And we want to add 5. I would actually be drawing this if I had good hands to use, but I don't. So I want to add 5 in here. So I want to make room and add 5 there. But this right here is creating a new node where this points to null. And that's where we get lost. Instead, what we actually want is to kind of take this piece here, and instead of null, give it that reference so that it continues on the list. And we simply do that by saying, okay, our node takes, remember we take this other reference, we actually have that reference, because if we haven't made it to the end, the current one would be the correct value. So current node, and we can print that before we assign it. Console log, current node. Let's run this. Boop. There we go. The current node data is 2, and it points to the next of 1. And so you can see 4, 3, 5, we inserted it, and we didn't lose the list. We have 2, and then 1, and then null left. So there we go. Okay. So insertion is fixed. We can insert anywhere in the list, theoretically. Let's just try and add a new one. Let's add 6 at the beginning, which would be 0, right at the head. It's the same as doing this. Right, so add 0, and then we'll add 1 at 5, let's say. Whoa, I don't even know if that's going to be there. That's probably a good test to do, though. Like add it at 10, what's going to happen? But I actually want to add something kind of in the middle, so let's do add set. This should be 7, this should be 8, and I don't know, 1. Like right kind of at the beginning, the first one in. Clear. Boom, okay. So 6 we added at the list, the beginning. 7 we added right after that, so we can kind of add them anywhere. Then the regular list goes on. 4, 3 are inserted 5 from before. 2, 1, and then, oh, awesome. That's kind of what I was hoping that it wouldn't break. But because I gave a number that was larger, our loop up here, this handled the situation where the index was too big for the list, which is good. That's good. So I just added it at the end. Awesome, so there we go. Look, we're creating this super long linked list. I hope you're like trying to see how inefficient this is to do all these operations, because you have to say, okay, if I want to add 8 in, I have to go like 6, 7, 4, 3, 5, 2. Oh, now I can add it after 1. So it might not be super efficient. Good. Okay. Print. So we can do all these adds. Now, all right. Now, what we like to do, because this is all adding at the head at the beginning and pushing them along, so they're kind of in reverse of what I'd like them to be. We got to fix it so that this loop actually works, even if before is null. Oh, there's an easy way of doing this, where we can keep track of the size, and we never have to worry about this current node. But I think we can do something just a bit sillier. Let's try this. So inside of here, forgets will always loop until the current is null. And I'm sure there's probably a way I can do this, but if we have a before value and the index is greater or equal 0, so we have some sort of value that's not null, I can just say it like this. It's not equal to null, just to be explicit. We want to actually check a different condition here. We want to say this is actually equivalent to 0. So when we actually reach the 0th, we've counted down and we hit the position we want, we're going to break out of that list. And that's what I think we should happen. So it shouldn't ever get here unless we have this index, and the fallback should be this. Let's try that. Let's try this. Yes, it worked. Okay, it's kind of hard to see. Let's just get rid of these additions here randomly in the list so we can see, clear that. There we go. So you have 1, 2, 3, 4, and then we'll add in 5 at position 2. So we'd expect it 1, 2, 5, and then 3, 4. Boom, 5, 3, 4. Brilliant, and then we can add in 6 at the head, so it should have 6 at the very beginning, 6, 1. Do that, perfect. 6, 1, 2, 5, 3, 4. 7, so it should be 6, 7. Because we on it at the first position. Boom, 6, 7, 1. There we go. And then if we could give something that's too big for the list, I'm assuming there aren't 10 elements here. I'm not going to count them. We can just use something crazy. 20, there's definitely not 20. It should put it at the end. Boom, look at that. Awesome. So now we have a linked list. We can add tons of elements to it, which is brilliant. We don't run into this weird problem where we're losing elements. It's not pushing them in weird order. That's super good. So the next thing, I guess, we want this to kind of be a useful data structure is the ability to, I'm just going to get rid of some of these comments over here, to remove items from that list. I'll close this up here. So we want to be able to give it some sort of, we can either give it like a piece of data, or we can give it an index. Probably an index is better. It's a bit easier to understand. We want to give it some sort of index to remove, and so that when we call remove, boop, I want to remove, this only takes one parameter, I want to remove the third index, that's add, yep, remove. That we have a list afterwards that has whatever was in the third index, so this is our list here, 0, 1, 2, 3, so this 2 should be no longer there. Obviously we've run it, that's not going to be the case. Whoops, run it. There we go. 2 is still there because we haven't written the implementation, but I expect 2 to be gone when we finish the remove. So let's try that. Remove, here we go. Let's close up the print, we don't need to see that anymore either. So we want to remove some index. Can you guess what's going to happen? We have to do some sort of looping and passing of values. Hooray! So the same thing, let previous node equal to null. Let current node equal to null. That's not right. Someone correct me. This dot head. All the billion people watching this stream, someone correct me. And then we're going to do while. Boom, just walk through. We'll do some conditions in there. What is it? Current node not equals null. Do some stuff in here. So previous node equals to the current node, and then the current node, whoops, is equal to the previous. Nope. What am I doing? Swapping them? That's crazy. Current node dot next. Get the next one. I hope someone out there is like, oh, why do you even have previous? Why do we need that? We'll explain in a bit. But this also isn't fully correct either because we actually care, most about this index. So we should say in here, similar thing to before, like if our index, and we can go with the same style of like minus, is less than, strictly equal to 0. So we've walked the list, however many indexes we are supposed to until we found the element, and then we have to break to stop this loop, this while loop. Again, I feel like this is a convoluted way of doing this. I'm sure I could figure out a way to put it in this condition here, but that's right. It works out for now. So if you find the index before the list ends, then break. Otherwise, we have to figure out how to remove the node that we're looking at. So over here, now removing a node is kind of funny. So if you have a list here, 1 points to, points to 2, which points to 3. I'm going to do the middle because it's kind of the most complex, I guess. And that was the end. And we want to remove number 2. If we just delete the element entirely, we actually lose, so let's just, replace this with a skull, of course. Skull. Boom, we killed it. Element number 2 is dead. What we actually do is end up severing this list and getting this. So now 1 is going to point to, I would hope null. I would hope we're smart enough to replace that to null. But really, it might just be undefined. Because we've deleted node number 2. And there's no reference to node number 3, which should still exist in the list. So we have to make sure that when we're deleting nodes, like this number 2, put it back, that we also create like a second, this is going to be weird to write, a second, maybe do, oh, here we go. Super crazy ASCII art. Boop, 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 boop. A second pointer to the number 3. And then up arrow. Let's just spend so much time on this. There we go. Boom. There we go. Perfect. So easy to understand. So 1, then 1 also has to go around and point all the way to number 3. And then we can delete 2 from the list, and it won't be a problem. It's completely gone, but 1 still points to 3. If I adjust my beautiful diagram. Oh my goodness. There, still points to 3. So we haven't really lost any data. So in order for us to do boom. Okay, I'm sure there's like a lot of holes in this if we try and hit some edge cases, but we'll try it just for now. We want to remove number 3, which in our list here should be this one. Let's go. Here we go. Boom. Oh, it worked perfectly. So we have 6, 7, 1, 2 is gone, we removed it, and we have the rest of the list. And I can show you what happens if we don't assign like the rest of the list properly. Oh, can we even do that? Like, can we delete? Not in JavaScript. All right, I ignore what I just said. Forget it. This is perfect. This is where all works perfectly. First try. Now what happens if we want to remove the head, for example? Remove element number 0. Please have an error, because that's what I would expect. An error. Cannot set property next of null. Cannot set property next of null. So I'm assuming it's saying the previous node is null. And let's walk through the logic and see why. So we start off here. Index here is equal to 0. Previous node is going to be null. Current node is going to be the head. We walk in here. Definitely not null, but we get in here and this is actually 0. So we've gone, oh, we should say less than or equal. Just in case we get, oops, oh my goodness. There, so it kind of gets in here, does the break. We haven't assigned anything yet. And then it goes out here and says, oh, but that's null. Because I haven't actually done this loop, this is null. So we actually want to like replace the head of the list. We have nothing before us. It's actually the head of the list, which makes it a bit easier if we just say, okay, well, that's not a problem. If previous node is, and we'll just actually just do some simple stuff here. It's not, if we don't have a previous node, it means I want to remove the head, which is the simplest removal, because all we have to say is this.head is equal to the current node, which is the current head, but either way, dot next. And that should remove our head nicely. And then this way we can say every other time else, it's fine just to remove it this way. So we'll always have a previous node after that. There, okay. Let's do this. Oops. Boom. Now, I don't know if this is right. So let's just print out before we do that removal. So l.print. There, okay. So we removed number 3, position number 3, then we moved the head, position number 0. There we go. So this is after we removed that 2 that was in between the 1 and the 5. And then we removed the 6, the head of the list, and we still have the rest of the list. If we didn't reassign this correctly, you'd lose literally the entire list, but we still have it. We have number 7 as our new head. The last kind of edge case is obviously removing the end of the list, and I'm not keeping the size of it So I'm just going to have to count this like one. Actually, we should just write a function to count it because I don't want to be bothered with that. So let's write a count. Let's put size. That's a good name. And again, we don't care about having a previous one. We just want to walk until we hit null and increment some counter. So we can say like let count equal to 0, and then let the current node equal to the head of the list. And then while we are walking that list, current node not equals to null. We haven't hit the end of it. We just want to say count, increment it by 1, and then make sure you actually walk the list. Oops. Equals current node dot next. Good. At the very end, we can just return count. So that should give us our size properly. Let's just comment this one out and instead console.log ll.size. Should count the number of items in there. Oops. Boom. 6. I hope that's correct. 1, 2, 3, 4, 5, 6. Perfect. So we should remove the last element in the list is just by giving the size and remove that one. I might have to do size -1, but we'll see. Then we'll print this. There we go. Boom. Yep. I have to do size -1. I went over the amount. No, you know what I did? Oh dear, this is even better. So it actually broke because at the end of the list, we don't have a current. We have next but no current. And I'm trying to like loop around. So we have to fix this code here a little bit as well. And say that if we have a current to use next, otherwise we just need to use null because we're removing the element before the end of the list. So we should have null. So this, we'll just do some ternary nonsense. So if we have a current node, use the next value. Otherwise, we're at the end of the list, and we want to just use null. So I'm pretty sure that's going to be correct. Ooh! I'm not typing in the right places. Here we go. Node, linked list. It didn't remove anything. It should have removed it. Maybe I lied. Maybe I don't need this. Let's do this. I think it's my issue is here. I'm trying to remove the size, but it's a 0-based index. So if I have 6 elements, I only have 5 indices, which means I need to take 1 away from that. And that should just work beautifully. There we go. No, I have 2 prints. That's why it's blowing up in my face. Run it one more time. You can get a nice print. Oops. There. So we removed 8, which is the last one in the list, by calculating the indice as opposed to the actual number of elements. 0-based index. Wonderful. So we can add things and we can remove things. The last thing we want is to be able to go and get some sort of value in that list. So let's close out the remove. So the get will pass an index. So I can say I want to see whatever value dot get is happening at position 2. And we'll console.log that. There we go. So we'll just get us whatever element exists at position 2. So we have some index and get. Same thing we've done a million times before. Create some values. In this case, we don't care about, again, we don't care about the previous one. We only want the one we're on. So we can set current node equals this dot head. And then while, I know, by the way, this is very bad by like doing index minus minus because I'm modifying some value that's passed in as a parameter. We should probably just copy it over or increment up to index and leave that constant. But I'm just being a bit lazy. Don't want to bother that nonsense. So we're just going to modify the constant variable coming in as a parameter. So current node not equal null. Oh, sometimes VS Code Y. There. And if that's not always the current node equals current node dot next. Now this obviously loop to the very end of the list until it's null and then return it. But we want to say same thing as before. If index minus minus less than or equal to 0, just in case for some reason we go over. We want to break out of that and return whatever the value of current node is. Return current node. Boom, first try, here we go. Oops, clear, clear. Bam, there we go. I'm assuming it's 5. 0, 1, 2, so it's 5. So here's the element 5 in the list. We get that data back here. We also, as you can see, get all the next references, which I don't really think we want to give people access to. So we just want the data from whatever that node is. I just want to know whatever position number 2 is, give me the data in that list. So let's just clear this. Oops. Boop, boop, boop. Boom. There you go. So number 5, that's the data that exists at position number 2. And we can do that. We'll say like position number 5. That should be the end of the list. Or, oh, it's too big. What happens if we went over? Oh dear. That's a good point. So I tried to get, because we went and removed element number 5, if I just print the size again here, or I can print the maximum index is what will be easier to understand. And then number 5, so it'll print something and then break. Oh, I didn't print anything because, right. Let's just not do this yet, not have it break. So the maximum index we can use is 4, but I tried to get 5. I tried to get 1 because I removed the position 5. So it says I'm trying to get it, but actually there's no data. So we have to say, if for some reason, we could count this and try and get the size and deal with that, but the easier thing would just be to say, okay, well, if I don't have a current node and this, so we say, okay, just return false if you don't have the data, otherwise return the data. So, or null in this case. Oh, yes, return whatever value this is, or that one, if that exists. So return null. But if we get 4, which would be the last element in the list, it should give us a value 4. That's convenient. The last element in the list is 4, the index is 4, craziness. What about the position number 0? Look at the very first one. 7 is the head of the list. There we go. So successfully implemented a very basic linked list in JavaScript with some pretty simple operators, adding things before and after, removing items, getting items, and then the size, and then some fancy print method. So, I mean, this would be a time where I'd ask, like, do you have any questions? But I don't believe anyone's watching this, or if you are, you're not in the chat. So if you do have questions, I'm posting this on YouTube afterwards. Just put a question in YouTube, or follow me on Twitter and ask me, because I would definitely be happy to answer those questions. I'll put all this code up on GitHub as well after this, so it can be available for everyone to look at. Good. Let's head back really quickly to some slides. So I was going to talk about linked lists and queues, decks and stacks. We covered linked list. No problem. That's done. Now, how can we implement a queue, a double-ended queue or a deck, and a stack using that linked list? Let's go ahead and do those. So let's create a new file here. We'll start with the queue. And we go with, let's use, yeah, we can use classes again. Class equals, that's not how that works. Queue. We don't want to construct, oh, we have to do constructor here. Constructor. You know what? How do I do, can I just do this? Can I just do like queue internally and then make it equal like that? Can I do that? Or would this break? Someone answer me. Queue. It'll break. Okay. I can declare this though as like a getter though, right? Get queue. Yeah. I don't think that's what I want though. Fine. Constructor. I'm trying to get it to be like a private variable so no one can access. Ultimately, we don't want people to access our queue from outside the queue. And then, actually, we need to actually bring in our linked list. Require, oh my goodness, typing linked this linked list. There we go. So then this actually will be a new linked list. Sweet. Let's just do a print method as well. Whoops. Which is all just doing this dot queue. Because it's a linked list, we can print it dot print. Because we already have a print on that. Now, before I run this nonsense, I'm not actually. Let's comment out all these things so we don't get a billion prints. Well, we don't want to do this either. Before we get any prints from our other files, and then we'll just do module dot exports equals linked. And we're just going to give it the class linked list so that we can use it in this file. Good, okay. So now I can do something like const queue. Haha, see it's a queue, but it's also a queue. Is a new queue like this, and then we can call console.nope queue.print. And that should give us a lovely empty linked list. So, up, boom. In case you're wondering what an empty linked list looked like. Just no, there's nothing there, there's no head. Perfect. So a queue, really briefly, what is a queue? Well, if we use JavaScript arrays to represent what a queue is, console.log, we have a list of things here. I don't even need to console log this, what am I doing? A list of things, and I want to, I guess the best analogy would be you're lining up to go somewhere, like you're queuing up at the bank or something like that. So you have person number 1, they walk into the bank, they go into the queue. Person number 2 walks into the bank, they go behind person number 1. And then as people in the front, as the teller, this is the teller. The teller there says, come on, next, next please. Doop. We pop people off of here from the front of the queue. So number 1 is going to get out of the queue and go and do whatever bank business they have with the teller. And when they're done, 2 will be popped out of the queue and go and do whatever business they have with the bank teller. What a ridiculous diagram. Good, so ultimately what we're doing is we're adding things at the back of the list, boop, and we're removing things from the front of the list. There is a name for this, first in. So if I come in here first, I am the first out. So first in, first out, also known as FIFO, first in, first out. That's the type of queue it is. Different bunch of different types of queues, but that's the one we'll be talking about. I'm going to leave this diagram up here because it makes absolutely no sense, and there's a cow, so let's leave that there. So the operations are obviously add and remove, or push and pop. We can implement those as a queue, so push that, and then pop. Boom. Pushing, it had to take some data. Obviously, we want to put some data in the queue. Popping does not care. There's no index. We can't remove specific items, and we can't get specific items. Brings me to the college days. Yes, Brian, that's the whole point. I'm surprised you're still here. I don't know what you're doing. All right. My head is actually getting sore. I'm thinking about all of these cues and things, so I'm going to try and hurry it up a little bit. Otherwise, no one will ever make it through this video. So push data, pop data, push things in, 3 being data, take things out. We don't care about an index. We're doing linked lists. So we have all the functions already from our linked list, like add and remove. So obviously in push, we're going to be using add. So we can go this.queue.add. Now, add, if we just did add and call it with nothing, if you recall, this will add it to the end of the list, which is not what we want. Just have what running in the background? What are you talking about, Brian? I'm so confused. I must have said something and completely forgot. So this is going to add it to the back of the list. I see. Okay. Right, you answered my question. Nice. I hope my voice is soothing to you then, Brian. You're having me on for like an hour. But what we actually want to do is push things on to the front. And we have a way of doing that. We have a way of saying, I want to specify an index that I want to place this thing before. And obviously the head is 0, so we're going to put 0. We want to always push things in the front, right at the head. So let's do that. Let's do a bunch of pushes. Q.push 1, and then 2, and then why not? Push 3. There. Boom. So 1, you can see, goes all the way to the end of the queue. Then 2 comes in, goes behind number 1, and 3 comes in, goes behind number 2. And then popping them off. So taking them off, having them go, is a lovely remove operation. Oh, pressing the wrong key. This dot q dot remove. And remove takes an index of the one we want to remove. And in this case, we always want to remove the one at the very end of the list. So we're doing this dot q dot size to calculate how many elements we have, and then get the indice of that, which is 1 minus the size. And remove that one. Whoops. 1, 2, okay, let's remove here. So let's do a pop. It takes nothing because whoever's at the front of the list gets taken off. So we should say we push 1 on, we push 2 on, so 2, so we have 1, then 2, and then we take 1 off. So we have 2 at the list, and then 3 comes on. So 2 should be at the head of the list, which is actually our end. But so let's clear this out. Whoop. And boom. There we go. So 1 is gone. He's been the cow. The cow has been there to take would handle his bank business. And then we do pop again, and we can keep calling that. It'll take off number 3. Boop. And I wonder if we call it like too many times. I'm curious now if I've written code well enough. Null. Okay, so we have nothing in the list. Where would we pop null? Yep. So I didn't check if I have nothing in there. So let's just handle that real quickly. Real quick. Let's go into our linked list. In our remove, over here. If current node is null, which means the head, we have no elements. Let's not do anything. So if the list is empty, this dot head, this is null, then we can just, whoops, return. We don't want to do anything. And I'll just write a little comment in there. The list is empty. Boom. Okay, so then this should not break anymore. Oops. Boom, perfect. So we can pop as many times as we want, even though the list is empty. It's not going to do anything. Perfect. All right, so that's queue. Pretty simple. Because we have a linked list, and we can choose where to add things. A queue is really just defining us an order, saying you can only add things in this side and only remove things from this side. The same thing can go for a double-ended queue. Like you can imagine, though, it's being able to add from both sides and remove from both sides, but there's still kind of an order to that. So let's take a look. Take a look how we do that. New file. Let's just copy the, oh, no. Yeah, I'm just going to copy this one. Boom, Q copy. dequeue, deck. Take the linked list in, change the name of the class to the deck. I'm just going to keep the internal variable called q, that'll be fine. Boom, okay, so now we have push and pop, and we'll get rid of this cow diagram because it doesn't really make sense here. We have push and pop, but we can have a push front, whatever side we consider to be the front. Then we can have a pop front, and we have a push back and a pop back. So let's duplicate all of these. Boop. Now, if you think about a queue, I think about, because everyone's lining up, you don't line up at the front, you line up at the back. So the original, for our queue, the original push we had is the push back now for a deck, which is this one here. And then the push front, this is big people button in the line, just walking right to the front of the line, which means in our case, it's the end of our list. So we're adding them, and we can do by default this one, adds to the end of the list. So there we go, q.adds, let's push front, the front of the queue, and push back is just a regular, like walking into a queue, walking into a lineup. Now pop, very similar situation. The regular pop is pop front. You take the off the front of the list, but we have to implement, so we can just do that here. Pop front, it's the old one. Pop back would be the other one, which would be like you lined up, and you're like, forget it, this line is too long, and you left. You pop from the back. And how we do that? We want to remove always the head. So just boop, remove 0. So there we go, push and pop, front and back. Let's just push front. So again, front of the line. So we'll push front, and then we'll push back. So we should add in, we'll just do 2 push fronts, so we can get some sort of middle element, and then we'll push number 3 in there, number 4, in the back, and see what that looks like. How about that? Not do all those million things as well. So we have a list. We push somebody in the front. We push somebody else in the front. So number 1 thought they were brilliant because they went in the front of the line. But then number 2 came in the front of the line and they got pushed to second place. And then we pushed 4 at the back. They were respectful and came in at the back of the line. Okay, printing. Here we go. Node, check, boom. So we have 1 kind of in the middle because 2 push them back. We push at the front twice. And then we have 4 coming normally push at the back. Now if we pushed another one at the back, 4 would also be in the middle. Let's do that. So we have 5 at the very end, 4 and 1 are kind of in the middle, and 2. Then we can do pop. So pop front. This is the thing, so we're 2 by the line. Now they're going to be off first. And then let's not do another push operation, but do another pop operation, and we're going to pop the back. So 5 came in, saw 2 go, was like, forget it. I'm just going to get off as well. Boom. So we had a lift with 4 and 1 because 2 left and then 5 left. There we go. Double ended queue. So you can add and remove from both sides. You still can't go into the middle and remove any elements. You still can't walk that list with any sort of index or loop. You have to just always be adding and removing things. Deck. Super simple. Linked list, man. It's like the way to go. It can do anything for you. It's just a garbage data structure, but that's fine. Okay, last thing, the stack. The stack, which would be even easier now that we've done a deck and a queue, doing a stack. Now what does a stack look like? Let's copy the queue file. Whoops, that's not the right one. Copy the queue file. Create a stack file. Rename this to be stack. And this one as well, new stack. I'm just getting so lazy, I'm just calling everything queue. It has push and pop operations as well. A stack, they're used everywhere in programming. You'll hear about them most often, like the function call stack or something like that, which we're not going to go into what that is, but it's used there. Stacks, really important. It is first in. So we're going to stack, element number 1 comes in, boop. Element number 2 comes in, it's going to go here as well, boop. Element number 3 comes in, it's going to go in here, boop. So we're kind of like a queue where we're stacking them in, but then we don't remove from the front. We remove from the same way we came in. So your first out, LIFO. Or you can say their way around is if you're first in, so that's number 1, you're the first one in, you are the last out. Philo. LIFO or philo? Completely useless acronyms. So when we remove it, 3 will be removed first because it was the last one put on. 2 will be removed. We can't touch 1 until everybody's gone, and then 1 can come out. All right, let's implement that real quick in using a linked list. So we have push, we have pop. Push goes all the way on, boom, boom, boom. So this is the same. I took this from the queue implementation. So it's the same thing. We're going to push them on like a queue. But then pop, where we're removing from the front, we actually want to remove always the head. Always the latest one we've added. 0. There we go. Okay, let's go over here. Our stack called queue, we're going to push on 1, 2, 3. Just for fun. 2, 3. Let's take a look at what that looks like. That's the wrong file. Node stack. There. So just like a queue, we have 3, and then 2, and then 1. That's the bottom of our stack. But then when we pop things off, unlike the queue, they will come off the top. So the first thing to pop will be number 3. So boom, 3 is gone. We have 2 and 1. And if obviously we pop again, let's do 2 more operations. So 2 pops, we'll have only 1 in the list. Here we go. That's it. We just implemented 4 data structures, 3 of them using our linked list, which is a super interesting, super, what do you call that, like diverse? I don't know. That'd probably be a bad name for it. Super flexible, that's it. A super flexible data structure, because you can build almost, I say almost, I don't actually know, but almost every other data structure with a linked list. I don't know how you would build a tree with a linked list, but I'm sure it can be done. I'm sure, I'm not gonna, I'm just thinking about trees, but I'm sure it can be done. I got in the talk, this is not gonna be the full talk, I went into like, what do we want to talk about, how they work, why do we not use them, and what are they good for. I don't really want to go through that right now, but you can take a look at my my website here, liststructures.now.sh, and see what I've written down. Kind of goes into some stuff. We talk about references a little bit. It's kind of useless if you're just reading through it, but we talk about references. And then, whoa, wow, what is this? The formatting's so weird. Then we kind of went through each one, why they're good, why they're bad. I didn't write down anything really about, we had a good talk in the meetup about these sort of things. But you can find all of my GitHub and Twitter and that kind of stuff at the end of those slides as well. Thank you for those who are watching, Brian. Cheering me on from work. But yeah, first stream. I feel like that's pretty cool. Look at that. It was so easy. I just did it. I don't know how to stop it though. I don't know how to stop this. I'm going to keep streaming. I'm going to be writing another, what should we call it? I'm writing a tutorial. What is that called? A workshop. I'm going to be writing a workshop that's coming up in 2 weeks in Ottawa at Shopify, and we're going to learn Next.js, the best thing ever, and Now. And we'll be showing you how to like launch. So that's what this is hosted on. Super easy, but which shows you how we can launch things super quick with Now. Literally the easiest way. Anyway, thanks for watching or listening, Brian. I will put the stuff up and tweet it out if you missed it. Thank you, thank you, thank you, thank you. Sweet.